Welcome back. Today we're going to be working on dilations and similarities, day number 2. Our content objective is students will be able to perform a dilation given scale factor and center of dilation. Our language objective is students will be able to explain verbally how to dilate figures using a coordinate plane. Why am I learning this? Well, it's important for real-world problems like creating video games. So to go over some background knowledge, just talk about all the things that all the different transformations that we've learned so far and the types of things that it preserves. So translation, here's an example of a translation. The segment lengths are preserved, angle measures are preserved, parallelism is preserved, perimeter is preserved, and area is preserved. And this is going to be true even with reflections. With reflections, again, segment lengths are preserved, angle measures are preserved, parallelism is preserved, perimeter is preserved, and area is preserved. And this is also going to be true about rotations. So once again, the segment lengths are preserved, the angle measurements are preserved, parallelism is preserved, perimeter is preserved, as well as area. And why are all these different things preserved? Because we know that all of these three types are considered rigid motion, which then means that the shapes, that the pre-image and the image are both congruent. Okay, now what about dilation? Well, dilation is a transformation in which the shape gets enlarged or reduced by a factor around a given center point. So is the segment length preserved? No, because they're not the same size. Are the angle measures preserved? Yes. Okay, they're similar. So yes, the angle measures are still the same. Is parallelism preserved? Yes. Is perimeter preserved? No. Why? Because the size is different. So you'd expect one of the perimeters to be either larger or smaller than the other. And what about area? Once again, the answer is no, because the size is not preserved, so you would expect both perimeter and area to be altered. So since the shape is changing size, it's not a rigid motion. The only ones that are rigid motions are translations, reflections, and rotations, which means dilations don't preserve congruence because it's not a rigid motion. Dilations, what it does instead is it creates similar figures. And again, similar figures are basically same shape, but different size. So two figures are similar if one figure is a dilation of the other. So in other words, there's one size, one's got to be smaller or larger than the other. Properties that are preserved under dilation include corresponding angle measurements are congruent, parallel lines remain parallel, slopes of corresponding sides are the same. Okay, corresponding side lengths is not preserved unless your scale factor is 1, because when the scale factor is 1, it means you have the same exact shape. Ratios of corresponding sides are equivalent and lead to the scale factor. So here it says LMNO has been dilated to obtain L prime, M prime, N prime, and O prime. So in this case, the dilation created a smaller figure. So you'll see here again, there's an animation there that the shape was reduced in size. So more dilation information. Corresponding vertices. They basically lie on the same line. So here if I were to connect L prime and L, okay, they're on the same line. M and M prime are on the same line, N and N prime are on the same line, and O and O prime are on the same line. They also lie on the same line as the center of dilation. So if I were to extend those lines, L and L prime, M and M prime, N and N prime, O and O prime, you'll see that they all touch in one point called the center of dilation. So the distance of the image vertex from the center of the dilation is equal to the scale factor multiplied by the distance of the pre-image vertex from the center of dilation. So here, what you're going to notice is that the scale factor is 1/2. So if you go from the center of dilation to L, in order to find L prime, you're going to have to take half of it, and you're going to notice it is half the distance. So segments connecting corresponding vertices, they intersect at the center of dilation. So again, if you were to extend the lines from L to L prime, M to M prime, N to N prime, and O to O prime, they will all meet at one point, and that's where the lines intersect, and that's called the center of dilation. Moving on to number 1, it says in the picture below, triangle ABC has been dilated to triangle A prime, B prime, C prime. So in this case, you can hopefully see that the dilation resulted in a larger triangle. So here it says part A to find the scale factor. So what I'm going to do in order to find the scale factor is I'm going to look at the ratio of corresponding sides. So the first one I'm going to look at is A prime, B prime to AB. So A prime, B prime, well, let's look at the length of that. From here, A prime to B prime, it is 1, 2, 3, 4, 5, 6 units. So I'm going to go ahead and write 6 over, well, how long is AB? Well, it's going to be 1, whoops, that's not the right one, 1, 2, 3 units long. So I have 6 over 3, which reduces to 2. Now I'm going to look for another pair of corresponding sides. I'm going to look at B prime, C prime, along with BC. So B prime to C prime, from here to here, how long is it? Well, it's 1, 2, 3, 4, 5, 6, 7, 8 units. So I'm going to write 8 over BC, which is 1, 2, 3, 4. So 8 over 4 reduces to 2 as well. Now the last point that I'm going to have to look at is A prime, C prime, along with AC. So this one's not as easy. I can't simply just count and get a number. What I'm going to have to do is apply the Pythagorean theorem. So here, if you look at the larger length, A prime to C prime, in order to do that, I'm going to have to use the Pythagorean theorem. This length I already know, A prime, B prime is 6, so I'm just going to write in 6. And here, B prime to C prime, I already figured out was 8. So in order to find this missing length, which I'm just going to go ahead and call x right now, I'm going to apply the Pythagorean theorem. The sum of the legs is going to equal the hypotenuse squared. So I'm going to write 6 squared plus 8 squared equals x squared. So we have 36 plus 64 equals x squared. This is going to be 100 equals x squared. Take the square root of both sides, and I'm left with x equals 10. So here, the length of A prime C prime is 10. Now I have to find the length of AC. So I'm going to go ahead and repeat this process, except for the smaller right triangle. First, from A to B, it is 3. So I'm going to go ahead and write 3 here. The length from B to C is 4. So again, to find this length, I'm going to apply the Pythagorean theorem. I don't know this length, so I'm just going to call it, let's say, y this time. I'm going to say 4 squared plus 3 squared equals y squared. 4 squared is 16, 3 squared is 9. Then 16 plus 9 is 25, so if 25 equals y squared, what is y? You're going to have to take the square root of both sides, leaving you with 5 equals y. So this length here is 5. So you'll notice here 10 divided by 5 is also 2. So I can come to the conclusion that the scale factor is 2. Now we do sometimes use r to represent the scale factor. So if I wanted to, I could have also wrote r equals 2. Okay, so now they want me to find the center of dilation. In order to do this, what you're going to want to do is go ahead and connect corresponding vertices to find where all of the lines intersect. So for example, let's go ahead and connect A to A prime. Well, they're in the same spot, so it doesn't make a difference. We're going to connect B to B prime, so that's going to create that line there. And then we're going to connect C to C prime, so that's going to create that line there. So you're going to find that all of the lines will intersect at this point here. So my center of dilation is going to be at 0, 0, which we refer to as the origin. Now it says to find the coordinate rule. It's good to understand that it is a dilation. And another thing about dilation, which is really good to understand, is you'll find that the coordinate rules is always going to follow the same thing. Whatever happens to x has to also happen to y. Okay, so one good way of understanding it is, hey, the scale factor was 2. And because the scale factor was 2, that means the x values doubled and so did the y's. So here is my coordinate rule. However, I do want to show you a different method. What you could have done as well is looked at the different ordered pairs. So for example, how did A become A prime? It went from 0, 0 to 0, 0. Unfortunately, this is not going to help us too much, so we can move on to the next point, which might be B to B prime. Well, B started with 3, 0, and B prime was 6, 0. What's happening to 3 to give you 6? Well, you have to multiply by 2. What is happening to 0 to give you 0? Well, anything can be multiplied to give you 0. So that's not much help. But so far, again, we do understand that whatever happened to x has to happen to y, so there's a good chance it was multiplied by 2. But let's go ahead and confirm by looking at C to C prime. C is 3, 4, and C prime is 6, 8. So here is a better idea. From 3 to 6, we had to multiply by 2. And then from 4 to 8, we also had to multiply by 2. So this confirms that our coordinate rule is the x's are multiplied by 2, and so are the y's. So the coordinate rule would then again be just 2x, 2y. Now looking at number 2, it says in the picture below, triangle ABC has been dilated to triangle A prime, B prime, C prime. The one thing that I suggest you do first is recognize, is a dilation creating a reduced image or an enlarged image? Well, first we start at triangle ABC, and then going to A prime, B prime, C prime, you're going to find that the triangle did reduce in size. Whenever it's reduced in size, you should expect the scale factor to be less than 1. And for the same reasons, if it is enlarged, you'd expect the scale factor to be greater than 1. So since this one has been reduced, we do expect a scale factor that is less than 1. So first what you're going to do to find that scale factor is to look at the ratio of the corresponding lengths. So first we're going to go ahead and look at A prime, B prime. So here's where you're definitely going to have to apply the use of Pythagorean theorem once more. So to find the length of A prime, B prime, I'm going to go ahead and highlight the right triangle that I see. I'm going to try to be as neat as I can. No promises there. So here we can see in this right triangle that one of the lengths of the legs is 2 and the other length is 1, 2, 3, 4, 5. So applying the Pythagorean theorem, we're going to get 2 squared plus 5 squared equals the missing length, which I'm just going to go ahead and call c squared. So we have 4 plus 25 equals c squared, 29 equals c squared. Take the square root of both sides, so we're left with the square root of 29 equals c. So here the length of A prime, B prime is the square root of 29. Now what about the length of AB? Well, let's see. I'm going to have to get rid of some of this work so that we can see a little bit better. I'm going to highlight the triangle that I see that forms the hypotenuse of AB. So here is the right triangle that I see. So the length of this leg is 1, 2, 3, 4, 5, 6. And the length of the other leg is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So applying the Pythagorean theorem, 6 squared plus 15 squared equals, let's just go ahead and call it c squared again. It's okay. We're going to get 36 plus 15 times 15 is 225 equals c squared, which is going to give me 261 equals c squared. Take the square root of both sides, and I'm going to be left with the square root of 261 equals c. So I'm going to go ahead and write that here, the square root of 261. Now here, I know this looks a little intimidating. What we're going to go ahead and do is simplify. I'm going to check to see if I can simplify both by a square root of 29, because if it does, that would be really nice. So let's check. 261, can I divide that evenly by 29? And the answer is yes. It does divide evenly. So here I'm going to go ahead and divide by the square root of, square root of 29, and divide this by the square root of 29. The square root of 29 divided by the square root of 29 is 1. The square root of 261 divided by the square root of 29 is the square root of 9. That is what's left over. So just recap, for those of you who aren't sure, I did square root of 9 times square root of 29 gives you this. So it's doable. So this is going to reduce to 1/3. Okay, so now what I'm going to do is go ahead, clean things up a bit, and do the next list of order pairs, which is B prime, C prime. So once again, I'm just going to highlight. So here you're going to notice that one of the lengths is 1 and the other length is 1, 2, 3, 4. So I'm going to apply the Pythagorean theorem. 1 squared plus 4 squared equals c squared. 1 squared is 1, 4 squared is 16 equals c squared. So 17 equals c squared. Take the square root of both sides, and I'm left with the square root of 17 equals c. Now we're looking for the length of BC. So that's going to be the larger triangle. So the length of this leg here is 1, 2, 3, and this length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So applying the Pythagorean theorem, we're going to put 3 squared plus 12 squared equals c squared. 9 plus 144 equals c squared. Then we're going to be left with 153 equals c squared. Oops, went ahead of myself. We're going to take the square root of both sides and be left with the square root of 153 equals c. So here we are going to want to reduce if possible. The best thing that could happen is if we can divide both by square root of 17. So let's check real quick. Can 153 be divided by 17 evenly? And the answer is yes. So I'm going to go ahead and divide by the square root of 17 to both. And I'm going to see that square root of 17 divided by square root of 17 is 1. The square root of 153 divided by the square root of 17 is the square root of 9. So once again, 1 is going to stay the same, but the square root of 9 can be reduced to 3. So far, it's the same number. Okay, so last but not least, let's go ahead and try A prime, C prime, and compare that to AC. So here's A prime, C prime. So here the length of this leg is 2 and the length of this leg is 1, 2, 3, 4. Applying the Pythagorean theorem, 2 squared plus 4 squared equals c squared. 4 plus 16 equals c squared. And then we're left with 20 equals c squared. So take the square root of both sides, leaving me with the square root of 20 equals c. So here, that length is the square root of 20. And what about the length of A prime, AC? Well, let's go ahead and shade that in. And go ahead and count that. The length of this leg is 1, 2, 3, 4, 5, 6. And the length of this leg is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here, let's go ahead and apply this to the Pythagorean theorem to find the missing length. 6 squared plus 12 squared equals c squared. 36 plus 144 equals c squared. Let's see, that's going to be 180 equals c squared. Take the square root of both sides, and I'm left with the square root of 180 equals c. Again, we're going to check to see if we can reduce. It's going to be a good idea if you can divide by the smaller number. So let's check to see if we can divide both of them by the square root of 20, and the answer is yes. Keep doing that. If we divide both the numerator and denominator by the square root of 20, you're going to get 1 over the square root of 9. And just again, so you can see, square root of 9 times the square root of 20 is going to give me the square root of 180. So this is going to reduce to 1/3. So you're going to find once more that the ratios for all corresponding sides are the same. It is 1/3. So in this case, I'm going to go ahead and say the scale factor is 1/3, and another way to write it would be r equals 1/3, because once again, we use r to represent scale factors. So how can you prove that these two triangles are similar? We can prove that they are similar by showing that the ratio of all corresponding sides are the same. It is 1/3. So now we're going to find the center of dilation. In order to do that, you're going to connect all corresponding vertices together. So I'm going to connect A to A prime. I'm going to connect B to B prime. And I'm going to connect C to C prime. The point in which all these lines intersect is called the center of dilation. So in this case, I'm going to go ahead and say that the center of dilation is at 0, 0, which once again we refer to as the origin. Now we're asked to find the coordinate rule. Definitely knowing the scale factor helps us a lot. So if you want to throw what you've learned from the scale factor into the mix of finding the coordinate rule, that's great. It's good to understand that the coordinate rule for dilation is whatever happens to x is also going to happen to y. So if you recall, the scale factor from earlier was 1/3. So in order to find the coordinate rule, you're just going to take 1/3 of the x, which means you're going to take 1/3 of the y. Now quickly, the other way of doing it is to compare A to A prime, okay, and B to B prime, and C to C prime. The only setback is when using the zeros is not going to be helpful at all. You're not going to be able to see how 0 became 0. So you're going to have to refer to how does 9 become 3? Well, you divide it by 3. Here, how does 6 become 2? Divided by 3. How does -6 become -2? Divide by 3. How does -6 become -2? Divide by 3. How does -3 become -1? Divide by 3. So that's another way of doing it, and understanding, hey, when you're dividing by 3, that's the same thing as multiplying by 1/3. So whatever method you feel more comfortable with, you choose. Okay, so for number 3, it says in the picture below, triangle ABC has been dilated to triangle A prime, B prime, C prime. Find the scale factor. At this point, what I'd like you to do is go ahead and pause the video and try this one on your own. Okay, so let's see. First, we need to go ahead and look at the ratio of corresponding lengths for each of the triangles. From A prime to B prime, the length should have been 8, and from A to B, it should have been 4. And this is just a matter of counting the units. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4. Plain and simple, which reduces to 2. And then here, we're going to repeat the process for B prime to C prime. So in this case, the length is 1, 2, 3, 4, 5, 6. And then from B to C, it's 1, 2, 3. So it's 6/3, which also reduces to 2. And then last but not least, we're going to have to compare the ratio from A prime, C prime to AC. Here, once again, you can't just simply count. You're going to have to apply the Pythagorean Theorem. So in this case, the length here was 8, and the length here was 6. You're going to get 8 squared plus 6 squared equals C squared. 64 plus 36 equals C squared. 100 equals C squared. And then you are left with 10 equals C. Oops, 10 equals C. So I'm going to go ahead and say that the length of A prime C prime is 10. Now I'm going to have to repeat the process for length for AC. AB was 4 and BC is 3. So I'm going to go ahead and put 4 squared plus 3 squared equals C squared. 16 plus 9 equals C squared. 25 equals C squared. Take the square root of both sides and we're left with 5 equals C. So 10 divided by 5 also reduces to 2. So you're going to see here that the scale factor must be 2. Another way to write it, once again, is by using r. So we can say r equals 2. So hopefully you got that one right. Now, again, to prove that these two triangles are similar, we went ahead and proved that the corresponding lengths have the same ratio, so they're proportionate. Now we're going to find the center of dilation. So go ahead and pause the video and try this one on your own. So in order to find the center of dilation, hopefully you connected A prime to A, B prime to B, and C prime to C. In order to find the center of dilation, you're going to look to see where all the lines intersected, which should have been right here. So I can say the center of dilation occurred at 5, 5. So this one, you'll see that the center of dilation was not at the origin. Number 4, quad QUAD is graphed below. Create a new quadrilateral that is 2 times larger than QUAD with the center of dilation at the origin and label the image. So first of all, we do remember that Q and Q prime should be on the same line. U and U prime should be on the line. D and D prime should be on the same line. And A prime should be on the same line. So keep that in mind. And because they want it to be 2 times larger, the scale factor is 2. So a good way to start is to first identify the different ordered pairs so that we can go ahead and just double them in order to find the new ordered pair. So first, what I like to do is create my coordinate rule. Since they want it to double, I'm going to go ahead and do 2 times x and 2 times y. In order to use this coordinate rule, it would be beneficial to know the different ordered pairs. Q is 2, 4. So Q prime is going to be double that, so that's going to be 4, 8. Let's go ahead and plot that right now, 4, 8. Here's Q prime. Next, let's look at D. D is 2, 2. So in order for this to be doubled, D prime is going to be 4, 4. Plot that point. So far, so good, because Q prime is on the line that's Q is lying on, and D prime is lying on the same line that D is. Repeating the process, U is, let's see, 1, 2, 3, 4, 5, 6. So 6, 6. So U prime is double, so that's 12, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whoops, 12's up here. And again, it's a good sign. U prime is on the same line as U. And last but not least, for A is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So 8, 4, which means A prime should be at 16, 8. It will be here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now going all the way to 8, which is right here. This is where my, let's see, A prime is. I know it's kind of lost in all the rest of the work, but there you go. That is what your dilation should look like. So it's definitely helpful to have a coordinate rule. It's definitely helpful to know the original ordered pair, so you can go ahead and use your coordinate rule to find the new ones. So how do you know your new quadrilateral is 2 times larger? Well, we can always compare the corresponding sides, find the ratio from the large to the small, and every single ratio should be 2. How could you prove that the 2 quadrilaterals are similar? Well, you can show that all the corresponding sides have the same scale factor or that they are proportional. That will prove that they are similar. So now it says create a new quadrilateral that is half as big as QUAD with their center of dilation at the origin and label the image Q double prime U double prime A double prime D double prime. So at this point, I want you to go ahead and pause the video, do the same thing, except this time, instead of using a dilation of 2, you're going to use a dilation factor of 1/2. Okay, so let's see how we did. So hopefully you wrote your coordinate rule as half of x, comma, half of y. So using the ordered pairs of Q, U, D, and A, you should have ended up with something that looks like this. And again, you'll see Q double prime lies on the same line as Q, D double prime lies on the same line as D, U double prime lies on the same line as U, and A double prime lies on the same line as A. And because the scale factor is smaller this time, which is 1/2, in this case is relative. If it's less than 1, your shape should be smaller, and which it is. So how do you know that the new quadrilateral is half as big? Well, again, you can go ahead and look at the corresponding side lengths, find the ratio from the new to the pre-image, and you should always get 1/2. Same thing of proving that they're similar. Simply compare and prove that the ratio from the short to the longer side is going to be 1/2 every single time. So that is going to conclude the lesson for today. Thank you so much for tuning in. And as always, until next time, bye.